Singapore. Just a little bit about my background. I was actually trained in statistics. I did my degree in Adelaide, South Australia, traveled around most of Outback Australia and Combidan, teaching agronomists about t-tests and analysis of variance and so forth. And somehow, years later, I ended up in Moscow. And I've always had like this little bit of shame about talking about statistician, especially in America. You say you're a statistician, people say baseball. But then, like about 2 years ago, in sort of the Silicon Valley area, which is where I live, there's this concept of data science rather than that. And for me, that was really, really exciting because I could say, I'm a data scientist. And people say, that's really cool. As opposed to I'm a statistician, they say, I'm talking to somebody else. So that's really what my talk today is about.
If you're a statistician, they seat you at the table with accountants.
Right. Yeah. Which we're the party at the accountants table. So that's really what I wanted to talk to you today, is about this whole concept of data scientists. Who's heard a lot about data science recently? Quite a few people. I actually asked that question to another group this morning, and I got 2 hands out of about 50. So this is a very different crowd. So I'll talk about sort of what I've been seeing in terms of what data science is and what it means, especially kind of in the West Coast area of the States where I live. And I've got a point to make. And the point I want to make is that data science is a philosophy, it's a methodology, it's a process that leads to a better methodology and better results in terms of analytics, especially with big data. And I'm going to contrast that with machine learning and try and make the case that machine learning really doesn't cut it in contrast to data science. Then I'll switch from philosophy into software and talk about the platforms that data scientists need and use to build predictive analytic models with big data. And I'll sort of finish off with a bit of prognostication about where I see big data going. One thing I'll tell you is that data scientists don't look like that. The data scientists I know wear skinny jeans and hipster t-shirts and things like that. So I get involved with a lot of hackathons in the Bay Area. People get together, work on Kaggle data sets, the Heritage Prize, look at community data, and do some really cool things with it. And that's actually one of the things that makes it hard to describe exactly what data science is. So let me try and do it by example by showing you a few data science applications that I think are notable. This is an application that was actually put together by one guy working at the San Francisco Estuary Institute. It's a government department responsible for water quality in the Bay Area. What they do is they go out and they sample water pollution by taking boats out to the bay and testing the water for pollutants and heavy metals and so forth. They dig down into the dirt at the bottom of the bay and test those for pollutants as well. They do air quality measures. And they represent the results of all these analyses in a really cool application that you can visit on the website's right here. It's based on Google Maps. You can zoom into a particular area of interest. You can choose a particular pollutant you might be interested in, and then have a look at the results of a statistical model, which is interpolating and predicting what the pollution is across the entire Bay Area based on individual point samples that have been taken across that space. So it's a really cool application that involves a combination of sort of web-based apps like Google Maps, statistical analysis, data visualization, and a lot of domain expertise about hydrology and solution, which is made quite accessible in this app here. So I think that's kind of cool. Here's another data science app that I think is interesting. This is put together by 2 guys, Mike Dewar and Drew Conway, out of NYU, New York University. There was, especially a few years ago, there really wasn't a lot known about what was going on in Afghanistan and the war there. It was kind of a big black box. But then there was this dump of data, which is the WikiLeaks data dump. This whole bunch of military documents, unstructured data. And Mike and Drew put their knowledge of intelligence and military records to good use by mining the WikiLeaks data and then identifying from it actual incidents of bombs going off and battles and friendly fire, and then being able to geocode them by identifying where they were actually happened from the unstructured data, and then plotting the results of that year by year. So these are the events in 2004. The different colors represent different kinds of events. 2005, 6, 7, 8, 9. This is a static version. They also put together a movie where you can see this animating over time. And it tells a really poignant story, I think, about the evolution of violence in the Afghanistan war over that time. Now, this is data that nobody would have seen otherwise had it just been remained locked in the Wikipedia analysis. And I think it actually turned a bit of the tide in terms of the sentiment towards the war at that time. Here's another sort of little more lighthearted example. This comes from the New York Times. The New York Times has an awesome data science team working in their graphics department. And they like to tell interesting stories with data, combining journalism expertise, combining access to lots of different data stories, and to data analysis, a lot of which they do in the R programming languages that happens. This is an analysis looking at the pop hits of Michael Jackson over time. We're looking at 1971 right now. You can interactively scroll across the entire timeline of Michael Jackson's music career here and have a look at each single, when it got introduced to the charts, where it rose to. You can see that Michael Jackson's first #1 single came in late 1972 and then hit #1 in about October or so. What's cool about this is not that it's a really interesting portrayal of a musician's career. What's cool about this is that it was news, because this application actually hit the New York Times' website 3 hours after Michael Jackson was reported dead. And so I think timeliness is a real aspect of data science, being able to tell these kinds of stories in a meaningful and interesting way. So it presents, what data science there is by example. But what do we need to be able to do data science? What are the 3 essential skills of data science? This is a sort of a concept that was first proposed by Drew Conway that I mentioned earlier on. It's been popularized by O'Reilly and their group. And I think it's something that's really held on in terms of, to make effective data science applications, you need a combination of hacking skills. And by hacking skills, we're talking about computer science skills, the programming skills that let you get your hands dirty with data. Find lots of different data sources that are available to build these applications, integrate those data sources together, mash them up with online applications and presentation tools like Google Maps, as we saw before, and build data applications that present the results of these analyses as an interactive story. You also need math and statistics knowledge. You need to know how to apply these algorithms and predictive methods to the data that you've got. This is what lets you build models, predictive models from data, to do meaningful visualizations from large and complex data sets, to be able to build predictions from data. And also, very importantly, I think this is one area that's overlooked a lot of the time, is to understand uncertainty and what an error bar means, and how to represent uncertainty to the consumer of these data analytics. And I think another part of this puzzle that you need is an understanding of the problem at hand, substantive domain expertise, so you know what the data means and where the data comes from and how to apply it to the problems that you might want to ask about the data sets that you're working with. Having expertise in a particular area knows what data sources might be available to actually apply to the problem, and where to find data that you can use to answer those questions. And it's the domain expertise that gives you the credibility to say, here is a prediction we've made, here's an estimate we've made, here's a classification we've made that's meaningful in the context of the data and the problem that we're working with. One thing that's interesting is if you take away any one or two of these expertises, these skills, you can end up in some interesting places. For example, if you're just, you're working in a particular area, you've got some data, you've got some computer skills, you know how to boot up a SPSS or something like that, you can go ahead and pump the data into a program. But without understanding the statistical methodology behind it, you can get yourself into some difficult areas, make predictions that don't make any sense, make classifications that don't make any sense. That's why Drew calls this the danger zone. I'm also going to focus on this area right here, this idea that if all you have is the ability to do computer programming, and you have access to statistical knowledge, but you don't know anything substantive about the data you're working with, that really puts you in the domain of machine learning. where the data you're working with is just considered as numbers or letters. You're not really relating that information back into the real world. And I want to talk a little bit about what machine learning means in a moment. But before I do, when you have the combination of all these three skills, I think that's when you're doing data science. That's when you can build effective data applications that tell a story about the data you're working with and have meaningful implications of what they can do. So let's move on to machine learning. Why do I say that machine learning alone isn't enough to build applications like this? And I think it's basically around this concept of working with a black box and why black boxes are important. I think I'm probably speaking to the crowd here, so I'll go through this fairly quickly and talk about just the basic process of machine learning, which is we start with data over here. But we just call this features. We just think of it as numbers. We have some kind of response that they claim to predict is associated with the numbers that we have. We apply some machine learning technique and we get a set of rules. And we can then use those rules and apply them to a set of data that we already know the answers to, like a validation set. And the whole idea about machine learning is to say, I want to find a set of rules that when I get predictions from them, they're in some sense close to the actual data that I already have. Validation. And there's some accuracy measure. There's lots of ways of measuring accuracy. Let's not get into that. But this is just kind of the gold standard of machine learning, is to make this accuracy measure as high as possible. So that when we get a whole new data set, we can apply the scoring rules to that data set, get some brand new predictions that we're confident in some sense are accurate. And I'll sort of show you some counter examples where I think this breaks down. The first example I'll give you is sort of related to a lack of perspective from just the predictions we're generating from. And the example I'll give is from the financial crisis of the last 5 or 6 years, when a bunch of physicists were recruited by investment banks to go to Wall Street. And their one and only goal was to take, for example, data about home loans and mortgages in the United States, and some data which we already had about whether those mortgages failed or not, or what the value of those mortgages were, and to build a set of scoring rules that best predicted what they'd already seen. They were physicists, so they didn't really relate the data back to people buying homes, moving into them, having value with them. It was just a set of scoring rules that best duplicated the data that they already had. What they didn't realize was there are a whole bunch of assumptions built into the data they were looking at. Mortgages in the United States had only been digitized for about 10 years. So there was only 10 years worth of historical data even available to them to be able to build those models. And so one of those implicit assumptions that was built into the data that they had was that the price of houses in the United States could never go down. Because it had never gone down in the last 10 years. It had 50 years ago. It had 70 years ago. But they never saw it. And of course what then happened was a black swan appeared. An event that hadn't been anticipated because they'd never seen it in that data. And that event was the price of houses did suddenly go down because of all the correlation that was suddenly inherited in the system from everybody implemented exactly the same model that said house prices were only going to go up. And that's fundamentally, in a very loose sense, what caused the housing crisis and the financial crisis worldwide. So a lack of perspective is what you get from treating data in a machine learning sense as opposed to in a data science sense. Like another thing you lose when you do machine learning without relating the data back to its source is credibility. If, for example, I was to go into a manufacturing organization that's producing products, build a model that said our product's going to sell this much in the next 3 months, and I was going to give that number to the salespeople in the organization and said, you're going to go and sell this much more product in the next 3 months because our model says so. Now, the salespeople are going to come back to me and say, why? Why am I going to take on this much extra quota? Why are you going to make me do this much extra work? And I'm going to say, well, because the model says so. And if I can't go back and say the reason why your numbers have gone up by this much is because we have so many new clients, we have this much more market, there's this much more advertising being done, unless I can give some kind of credible justification to it, the chances of somebody adopting the predictions that I make are just so much lower. When we use data scientific methods, when we can relate it back to the source information, we can make people believe what we say and adopt the model we produce. I want to give you one sort of very personal example about this, and that's about 3 months ago, I cancelled a credit card that I had for 10 years. I've been with the same bank, I said I was at Citibank, I was with them for 10 years. And then suddenly, about 6 months ago, every now and again when I went to buy something online, like I went online to buy a case of wine, they would randomly void the transaction. And I call up and say, why? And they said, that was fraud. I said, no, it wasn't. I was buying wine. And I said, no, it's fraud. And then I'd say things like, well, can you tell me why you would go ahead and call this transaction fraud? And they'd say, no, we can't tell you. I don't know why. I don't know whether that was just policy. I don't know whether sort of the agents on the phone just had no idea. But if they had been able to say to me, the reason why that transaction was avoided, because historically the number of people that were buying from that particular vendor turned out to be fraudulent, I would say, well, that's fair enough. You know, I don't want to be part of fraud. But because they couldn't tell me anything about it, because they had no credibility, I was furious and canceled the credit card I had to send. One more example about machine learning, and that's that machine learning methods can turn out to be really, really complex when it comes to implementation. Who's heard of the Netflix prize? Just about everybody here. What you might not know is that Netflix never implemented the winning prize. They actually implemented the second best prize. They had a look at the winning prize. It was actually an amalgam of about 30 different models through a model averaging process, and decided that the amount of time and expense it would take to re-implement that model in the systems that their sort of operational systems use far outweighed any benefit they would have gotten in improved recommendations.
Sorry, what was the competition for?
Well, the competition was to build a model that better predicted the movies that somebody would like to watch through a recommendation system than their existing system at the time. So they did end up implementing the second place one. But the interesting thing is that it wasn't just the complexity of implementing that system that was the problem. It was in the intervening years between when the competition ran and when the winner was decided, Netflix's business model changed. When the competition began, they were almost exclusively a business of sending DVDs out to people. And by the end of it, they transitioned to a business that was almost, a lot of the data was coming from streaming, watching videos online. And so they had all this extra information they could use about not just which DVDs people had ordered, but actually which videos they clicked on, how far they'd watched into them, whether they fast-forwarded, if they switched to anything else. And because of the complexity of the models that they were using for recommendations based on DVDs, they couldn't incorporate this new information into streaming data, and essentially had to start it. So my contention here is that a process around data mining, the golden unicorns in the sunset, can improve things in several ways. And I think one of the things that makes data science different from data mining and from machine learning is that data science lets us answer questions that we haven't even thought to ask before. Machine learning has a very specific goal. You remember that accuracy I was talking about? It's just around making those numbers match up as best as possible. So we define the question rigidly in advance. But the whole idea about data science is exploring data, playing around with data sets, looking at relationships, doing visualizations, doing data exploration, and discovering things in the data set that you might not have thought about. The example I'll give you about that is Target. Target is a big retailer in the United States and around the world. And they had a data science team focused around looking at the loyalty card data, the point of sale data, the inventory data, the pricing data, all the other data sources they had, and said, what can we learn from this in order to improve our sales fundamentally? And the team there had looked through the data and discovered something quite interesting. They realized that there were patterns of people purchasing certain things like baby clothes, baby equipment, and discovered that with enough modeling, they could actually identify which of their customers were pregnant, and in fact pregnant in the very early stages of pregnancy, in the 3rd month. And this is important to retailers because that's the point at which you can switch brand loyalties, transition people onto new products, generate new sales that might not have come from anywhere else, because for the first time they're choosing a retailer to provide a whole new class of products they haven't purchased before. And they were able to do this very, very successfully. They were able to identify customers that were pregnant in the very early stages, send them coupons and offers for baby equipment, which are then coming to Target and buy. A couple of interesting stories about this is number one is that when they first implemented this, they got a phone call from the father. They called up and said, "Target, what the hell are you doing? You're sending my poor innocent daughter all these coupons as if she's pregnant. You know, what's all this about?" And they said, "I'm sorry." And then he called back a week later and said, "You know, I just learned something. I want to apologize for that abusive call from the last week. There's been a change in the family because Target had learned that his daughter was pregnant before he knew." So this stuff, really works. The other interesting story, which is kind of a more practical lesson, is that it works, for that particular person, but they also discovered that a lot more of their female customers will also get creeped out by this. What right does Target have to know that they're pregnant when their friends don't know it? Why are they sending them all these coupons? It's creepy. So they fixed the problem by, even though they were still doing these targeted campaigns towards pregnant customers, they were mixing in the baby coupons with coupons for lawnmowers and air conditioners and pogo sticks and all this kind of random stuff. So they didn't realize it was targeted towards them, but they were still getting the offers that made them come into Target. Besides exploring data, lets us answer questions we might not have been before. Another thing about data science and what it lets us do is to fill in gaps in the knowledge and the data that we have. There's a very famous quote from Google. It's in a form of a paper down here, but Google was famous for saying that algorithms don't matter because it just matters getting more data. More data beats better algorithms every time. And that kind of goes down to the heart of statistics. And you don't need statistics, you don't need forecasting when you know everything, when you have all of it. And Google knows everything. Google has data about all of us in any kind of detail about where we've been and what we've done. And a lot of the analytics in Google, not all of it, but this particular case, it's really just a matter of counting the data or looking up in the data. But very few companies have databases like Google. Most of us, even if we have big data, have aspects or pieces of the information that are unavailable to us. And that's where data science and statistics can really help. Like Tim O'Reilly put it well. Companies that have massive amounts of data without massive amounts of clue are going to be displaced by startups that have less data and more clue. So in other words, using statistical methods, using data science, is going to help a lot of companies to be able to infer information from sort of the lacunae in the data sources that they do. Lastly, I think something that data science does for us that machine learning doesn't is it provides context. Let's just take actions. To give you sort of a counter example to this, I can quite easily predict the S&P 500. All I need is the rate of butter production in Bangladesh, United States cheese production, and the sheep production in Bangladesh and the United States. It's 99% accurate. This is from a paper called Stupid Data Managers. That might be well and good, but it's not very useful. It's not going to let me infer anything about the stock market based on these statistics that just happen to be correlated with the S&P 500. I think what's different about data science, when we have variables that we know are related to the prediction at hand, is that we can have understandings about what does influence the sales of our products, what does influence the loyalty of our customers, and use that information to change our business practices. So we even do things like make experiments. We can distinguish between correlation versus causation, where we can actually change the variables. Now we can only change the variables when we know what's influencing in the first place. And that's why, again, it's important to relate the source data back to the real So with that, let me turn from philosophy to practicality and talk about, what do we actually need in terms of platforms and tools to make these data science types of applications work. What is the data scientist toolkit? I would love to have a supercomputer in a briefcase. That's not quite enough. But let me start with data. It's obvious that you need data to do these kinds of things, but I think the lesson I want to take away from here is that I think in all the data science applications I've looked at, blogged about, reported on, 0 of them have started with doing a query against a relational database and getting a nice rectangular table of data to work. In my experience, and I think this is something that distinguishes the data science process from some other types of processes, is that the data you start with is going to be messy, and it's going to come from lots of different sources. I would say that 90% of the data that I've seen in these applications has started off as an ASCII file. Generally huge ASCII files, processed with set or awk or Python and decompose and process. But a lot of the data you're working with just sits there in ASCII. A lot of people are now dumping data like that and also sensor data and information into either Hadoop, very cheap and efficient way of dumping data, not particularly performant, or in situations where performance is important, data appliances like Teradata and Teams and so forth, more so on the corporate side. But we can't forget that there are sources of data outside of the building that are relevant to all the problems that we're trying to solve. There is data available through APIs. Yahoo is an amazing network of APIs where you can find social data, geolocation data, demographic data, which you can apply to these kinds of problems. There's all sorts of data on the web, and with some simple web scraping techniques, you can get useful information from there as well. And then, of course, there's the world of social data, downloading data from Twitter, through Facebook's APIs, and so forth. You can apply to these types of problems as well. It's a messy process. There's a lot of work there. Typically, this is 80% of the problem. But finding new sources of data and incorporating them is part of the data science process, and I think it's very important. Next is, what do we do with that data? How do we do an analysis? And we need a platform. We need an environment to program with data, to apply all these exploration methods, all these data sources, all these statistical methods to the problem. I think R is an awesome language for doing that kind of thing. I've been using S and R for many, many years, so I'm very, very biased at this point. But I've tried to use other things. And R is the only language that lets me think as a data scientist. It works in the concepts that I want to work with, data objects, and data frames, and models, and graphical elements, that I don't think exist in any other language. I'm not going to go into details of this. If you want to sort of read all my arguments about that, there's a white paper I can refer you to right there. For anybody that hasn't played around with R in detail, just let me give you an example of the kinds of things you can do with it. This is from my friend Drew Conway again. This is working from data from data.gov, the US government's public data repository, looking at where across the country are grants being awarded to homeless veterans. This was done in honor of Veterans Day last week. There is a public data source for that. It's kind of messy. It doesn't have latitude and longitude in it. It has written down addresses, all sorts of other messy aspects to it. But just some points. Within R, we can read that data in, restructure it into aggregations by cities and states and city centers. We can define a function which will translate a written address to a latitude or longitude by interfacing it in with the Yahoo geolocation API. We can then run that across all the data through iterations and then represent the results using some custom graphics. So this is 25, 30 lines of code. I think Drew put this together in maybe an hour or so, going from a raw data source into a nice visualization of data. And for me, R is the only language that lets me sort of do this kind of thing without stumbling through roadblocks or twisting myself into contortions of the language. I think another thing that a data scientist needs is speed. Lots and lots of speed. And the reasons might not be as obvious as might seem from that headline. Just let me summarize the process. We start with data, and then we want to build a predictive model. the building a predictive model isn't just pumping the data through a black box. It's an iterative process. There are various ways we can select from the data, or do aggregations, or do transformations. Transform up the variables lots of different ways. There are lots of ways we can estimate the model and narrow it down and refine it, make it more parsimonious. We can compare that model to other models we've tried or other types of benchmarks, and then we can start again. Work with a different form of the data, or just do different kinds of models, compare those. The data science process is about iterating around this several times and refining and exploring and then building the best model. And so ultimately we get a model that we think is going to generate good, incredible predictions. R is a language that lets us go around this circle in a very efficient manner, because all the building blocks and pieces you need to go around this circle are already there. So just from a programming sense, R lets you do this quickly. Also, there's how much time you have to wait every time you actually pump data through this thing. And that's especially an issue when you work with big data. If you have to wait for longer than a cup of coffee every time you go around the circle, you're not going to go around that circle very many times. But the more times you do go around, the better things are. So it's important to make that cup of coffee a short one. So just to say that's something that we focused on a lot at Revolution Analytics with respect to R, is to make sure, for example, that when you do these kinds of analytics, it can use all the processes that are available on one machine and parallelize the problem to make it run faster. Like I said, that's especially important when you're working on big data. And one thing that I've been working with R and big data for several years now. We had a big project, an ongoing project, to make all the statistical building blocks, the models like regression and clustering and neural networks and trees, work with big data. I thought all these algorithms were out there already.